Jupyter notebooks as an electronic notebook to store and share computational chemistry. But I should say from the outset that I'm not a computer programmer and I'm not a computer scientist. My background is actually in organic chemistry and medicinal chemistry. And in 20 years at Merck, I led a number of medicinal chemistry projects. But during that time, became more and more interested in the computational side of things and ended up being responsible for computational chemistry. During that time, I dabbled in lots of different scripting and programming languages. But again, I come from the cut and paste school of programming and not really a dyed-in-the-wool programmer. What I did notice, though, was that there is very little support for chemistry within most programming languages. And so when I started consulting, one of the things I wanted was a way of actually building computational models, but also being able to share them. And so I looked around, and what caught my eye was Python. From a scientist's point of view, most of them are not programmers, and so what they want to be able to do is get data from experiments and things like this, manipulate it, process the data, visualize results, build models, but also they want to be able to view chemical structures and generate high-quality plots and graphs for publications. And they also want to be able to share the results of the analysis to allow other people to repeat it, but also to build on it. And whilst you can cut and paste from a command line, it's not usually the best way of doing this sort of thing. So what caught my eye in Python was it's well structured, the syntax is relatively simple and readable. Many other languages are often described as write-only because once somebody's written it, other programmers find it very difficult to read. Most of the scientific routines that you might want to do the analysis, like NumPy, SciPy, are all readily available and freely available. And it seems that Python is gradually becoming the lingua franca of cheminformatics. Most, if not all, of the cheminformatics toolkits that are now available have a Python interface. Whilst you can use Python for developing data analysis scripts, you can also use it for building applications. As I say, it's free. Many of the things are open source, widely spread and used. And the other thing from my point of view is that there is a very vibrant community that provides very rapid and efficient support. I noticed this survey that was on the KD Nuggets website from middle of last year, looking at their annual analysis of what are the most popular tools that are used in data analysis. I should say this is data analysis professionals in general, not cheminformatics. But what is clear from the left-hand side is that whilst R is one of the major players, Python is rapidly coming up. And if you look at the second column there, percentage change, I suspect that it will supplant R as the most common data analysis tool. And on the right-hand side, you can see in terms of general programming languages, Python again is very, very popular. So from my point of view, this seemed to be the best choice for getting a vibrant support and also a useful tool set. And then that really brings me on to why Jupyter. As I say, you can cut and paste code and put it into emails, but that's not really a good way of sharing it. And these two scientists, computational scientists, also had obviously the same problem, and they developed the iPython notebook. And they wanted to share code, and particularly they wanted to share it in a format which allowed other people to read about what they were trying to do, but also build on it and use the notebook without any real difficulties. The I in iPython actually refers to an interactive command window, and the nice thing about the iPython notebook was that you can interrogate various cells at different points and find out exactly what's happening with the code. And you can get very easy access to call up data analysis packages and to introduce plots and displays. This has now been moved to the Jupyter project, which aims to make iPython more compatible with other languages, including R and Julia, etc. If you want to find out more about it, I'd very much recommend that you read this reference in Nature. And particularly, I put a quote here that I think really underlines the reason why iPython and Jupyter has been so successful. It allows you to do this iterative programming where you can add blocks of code, but then punctuate it with bits of prose, images, etc. And so it really excels at demonstrations, research, and teaching. It allows you to describe your thoughts as you're actually doing it, and then add various code blocks. So what does it look like? Well, actually, it's one of the really nice things about it is that the user interface is actually a web browser. So everybody's very comfortable and familiar with this. And what it allows you to do is to have various blocks that do elements of it. So there's a block here that has just a bit of text explaining what the next piece of code is going to do. You can add code into it, spreadsheet type functionality. You can plot images, in particular you can plot chemical structures, and you can plot graphs, histograms, etc. All the sort of things that you would want in a notebook. And the nice thing is that you can run it and view the results all within the same page. So how do you install Jupyter? By far and away, the easiest way of doing this is to use one of the package management systems. There are two main ones for Python, pip and Anaconda. I use pip largely for historical reasons, and if you're using pip, you install Jupyter by just simply typing in a terminal window, pip install Jupyter, and it will install Jupyter plus all the dependencies. Once it's installed, you then type Jupyter Notebook in a terminal window. The interface will open in your web browser and you can start coding. So it's really trivial. What I thought today, I'd give you 3 examples of notebooks. These are in increasing complexity, but they actually build one upon the other. So the first one is actually the first notebook I wrote, which was to access data from the Open Source Malaria project. Then another one which takes an SD file that you have locally, calculates physicochemical properties, and then plots a series of histograms and graphs. And then finally, one using machine learning to predict Ames activity. So the Open Source Malaria project is trying to find a cure for malaria using open source principles. The landing page, I've shown you the URL here, and it gives you the summary of the most recent activity on the project. All the data is in the public domain, all the ideas are freely shared, anyone can participate, and there are no patents. So the tagline is Linux for malaria research. Whilst everyone can see the data, and they can see all the compounds that are made, and all the biological and physicochemical data that's been generated on the compounds, it's often spread over multiple web pages. And so it can be tricky to link a molecule with the corresponding identifier and with all the data. So over the last few months, there's been a significant effort put into populating a spreadsheet with all the information. Of course, we want to be able to share this spreadsheet, so what we did was put it into a Google Docs spreadsheet, shown here. This spreadsheet anybody can access providing they have the URL. And as you can see, it's got the IDs of the molecule, various identifiers for the molecules, smile strings, and then different measured activities. It's actually about 75 columns. So what's this first notebook going to do? It's going to read the data from a URL, import it into a data frame, and then display chemical structures and plots. So if we start, here we go. So this is the notebook. At the top here, you've got the usual sort of commands that you would want to be able to do for opening and saving files, cutting and pasting, and then you can then insert cells above or below the cursor to add little bits of code. So the first bit of code we've got here is wget. This is a computer program that retrieves content from web servers. So you can think of as get from a World Wide Web resource. If we just run that, It goes and gets the data and then saves it to this export file here. You can see that it's retrieved 155K of data, and it took less than 0.1 of a second. The nice thing about this is that because you're doing it this way, this is up to the minute data. This is the spreadsheet as it was last updated. We then import a number of Python modules. RDKit is a cheminformatics toolkit. Pandas is a open source library providing really high performance and easy to use data structures. You can think of this as a sort of spreadsheet for storing data in. So we import those. The next bit is matplotlib inline. That just gives us the ability to include images, etc., within the notebook page. We can, at any point, we can have a look at the data file. So this data file.head5 shows us the first 5 rows, and as you can see, there they are, all inputted from the spreadsheet. There are 75 columns and the first 5 rows. We can interrogate that spreadsheet even more by taking one of these small strings and converting it to a structure in a format that chemists would like. So first of all, we create a variable from this cell, then create a molecular object from that small string, and then we can display it. And as you can see, it's displayed the structure here. And just to show you that this is live, I'll just change that to a different structure. Do the same again, and again you've got a different structure this time. At any point, we can then take one column of this data and create a spreadsheet, a histogram, as shown here. So that's all well and good. That's a relatively simple notebook for accessing data from a URL. In general, you don't have that, and so what I've got here is another example where you're using a local file and using it to calculate properties. But again, I'll be using a lot of the same tools, in particular the DataFrame, to store data. So you read in a file, calculate properties, store them all in a DataFrame, and then we're going to display chemical structures and plot results. So again, going back to the notebook, this is calculating the properties. So there's a couple of things I think which I should emphasize up front. One is that the file that I've used to generate the structure that I'm using to calculate all these properties was first imported into Mo, which is a molecular modeling package. And I use this because it's got very nice features for washing the structures, getting rid of incorrect structure or flagging incorrect structures, getting rid of incorrect tautomers and protonation. So they're all tied up with that. And I also added another field called ID number. Whenever you're going to be doing any form of cheminformatics, one of the most important things is to have a unique identifier for each record. And so I sort of got into the habit of putting ID number in there and a unique, so making sure I have a unique way of identifying compounds. This will become more, the importance of this will become more apparent later. We're actually going to use another tool to calculate the properties, and that's the evaluate program from Chemaxon. So let's just go through this. So I've imported a whole range of modules from Python. So pandas we've talked about, NumPy and SciPy are scientific modules, RDKit I've mentioned, and the other one that I'll come back to is Subprocess, and I'll do that in a second. So the file is here, and what I do is import the file path here, and then I'm going to start using Subprocess. Now, Subprocess is a module that allows you to spawn new processes. It's a way of connecting to command line applications, so you can pipe your data to it and then capture the output. So here we are creating a subprocess to this Chemaxon evaluate program, which is actually a Java program, but it has a command line interface. We pass it all of these variables, and we're going to get it to calculate log P, log D, pKa, polar surface area, percentage aromaticity, and what we do is then capture the output. So that all then goes into this variable output. One of the issues with a number of these things is that they quite helpfully add thousand separators, so you get commas into large numbers, and we have to replace all those to make sure they just go to, otherwise occasionally they can get interpreted as text rather than numbers. We then do that, and then we then import that into a data frame as before. In this case, the Chemaxon program uses the semicolon as a separator, and we create all of these columns and import it. Again, we can check that everything's imported correctly by looking at the first 5 rows, and as you can see here, you've got the ID number, smile strings, and then all of these calculated properties. One of the things that we've calculated are these most acidic and most basic pKa's. And whilst that's interesting, actually what we're perhaps more interested in is which ones are ionized at physiological pH. And so we can just set up a simple calculation to add new fields for base or acid depending on the pKa relative to a pH of 7.5. Now we've got that, we can actually go through and categorize these molecules to be either acids, bases, deuterines, or neutral, and we do that as to whether based on the column whether they contain an acid or a base. And so you can see now we have all of the same things as before, ID numbers, all the properties, but here now we've got extra columns with either whether true or false for base and acid, and then the category for acid, base, neutral, deuterine, etc. As I mentioned, the original file I generated in Mo had a couple of properties that had already been calculated. These are normalized principal moments of inertia for giving a measure of 3D shape. So you can see here, after importing them in, we've got the ID number, this is the molecular structure, but also these 2 other properties which we want to include in with all the others. So there I've calculated properties using external programs, either Mo or the Evaluate from Chemaxon. You can also write the programs within Python itself, and so this is one for getting a plane of best fit. This is contributed by a user, and so anybody has access to it. And again, it's another way of evaluating the 3-dimensional structure of a molecule. I won't go into the details of how that works, but just say that once you've loaded that, you can then apply it to the data frame, and you can see here we've taken all the structures and calculated a plane of best fit. We now have several different data frames in which we have some different properties. So we've got one with the plane of best fit, one with the normalized principal moments of inertia, one with all the calculated physicochemical properties. And what we want to do now is merge them all together. If you remember, that one had the plane of best fit. One thing that is often a good idea is that these ID numbers, occasionally, as I say, you can get 1,000 separators into them. So I just go back and make sure they're all there as just as integers, and then we can merge them. So here we merged 2 of the data frames using the ID number as the key. And when we do that, we've got ID number, smiles, calculated properties, and here you can see we've now added on the plane of best fit. We can carry on adding more of them. So here we have plane of best fit here, and then all these from Mo. So we've got the normalized principal moments of inertia. We then come to the point where we actually want to plot these, so we can select which variables or properties we actually want to create the plot from, and then we use a combination of MATLAB plot Matplotlib and Seaborn. Seaborn is built on top of Matplotlib. It gives you a way of constructing really quite high quality plots with relatively little coding. And so here you can see the result. We generate a plot for all of those. Again, the nice thing is that it's plotted within the notebook again. As you can see, we can plot continuous data quite comfortably in a range of histograms. Here we have one which is categorical plots for acid, base, neutral, zwitterion, and here we have a scatter plot. So all different plot types. And finally, what we can do is we can save that as a PNG, and then you can put that into reports or web pages or whatever you want to do. So that's that one. The final one is Ames prediction. This again is built on all the things that I've talked about beforehand, but it incorporates the machine learning. So what we want to do is import structures from an SDLF file, calculate properties, fingerprints, combine them together and merge them into a single data frame, generate training and test subsets, generate the model, and then use that to predict a test set. And then we can use that model to predict activities for either a single molecule entered as a SMILE string, or as use it to using a file of structures imported as an SDF. But most importantly, perhaps, we can also save this model for later and share it with other people. So going back, so the first part of this I've already run through because it uses this data set from this paper here. It's about 6,500 to 7,000 molecules, so it would actually take quite a while for me to do the calculation on the properties. But all I'm doing is the same thing as I've done before. So we import all of these modules. The only new ones really here are scikit-learn, which contains all the it gives you the ability to do the machine learning processes, and also this pickle. This is, I guess, is sort of the sort of humor of programmers. Pickle is a way of preserving computer models. So as before, we read in the data, and then here, this is this block here is all the same as I've done before for calculating the physicochemical properties using evaluate, and then classifying them into acids, base, etc. You can see that the structures are here and all the properties that you've seen before. The original Mo file is shown here. This contains the Ames activity. And obviously, when doing the calculation, whilst we have all the properties, we don't have the Ames activity. And so we need to merge it using this unique identifier again, ID number. Again, we merge them there. So we have the ID number and all the properties, and tagged on the end here now we have the Ames activity. I'm just showing you the first two rows. To calculate fingerprints, I'm actually going to use Morgan fingerprints. These are circular fingerprints so that for each atom you take into account the atom types, etc., of the surrounding atoms or connected atoms. You do this all within using tools within the RD kit, and this is the Cheminformatics toolkit, and this allows you to build a data frame containing a column which contains the fingerprints. As you can see here, it's not particularly exciting to look at, it's quite a sparse fingerprint. We then select what we want to use for the model, and these are all the cells that I've decided would be important to activate in there, and then we set up a data frame for the model. So this is a data frame for machine learning, and the target activity is the Ames activity. We then divide that into a training and test sets, as shown here, to split them, and you can see that this contains all of these 2,500 fingerprints. The part where you actually generate the model is just here. So this is a random forest model. So and you can see here we're using this is the starting point we're using for the model, and we're using the training set to actually build the model. This part here I'll come back to, but is where we actually save the model using Pickle. The nice thing about doing this is that if anybody else wants to use it, they don't have to go through all the process of calculating the properties on those 7,000 molecules. We can test the data set by using the test subset that we had generated. So here we predict using the test data frame, and then we create a confusion matrix. So this just gives you an idea of how well the model's doing. So here for the inactives, it's the prediction is 236 of them, 56 incorrectly predicted, and similarly for the actives. So a reasonable prediction. If you actually want to interrogate this more in more detail, what we can do is we can rename the column that actually had the prediction from simply just 0 to prediction, and then display it like this. So where it's a 0, it's not active. Where it's a 1, it is active. We can then combine that with the original data frame that we had from the test set, and what we can see, if we combine them, just looking at the first 3 here, this is the predicted activity, this is the Ames activity from the test set, and as you can see, that the first 3 there matching up quite nicely. And you can then export this to a CSV file, and you can then interrogate that in more detail, perhaps looking at the compounds where the prediction has failed to see whether these are chemotypes that have some unusual property that mean that they're not like the rest of the data set. We then come on to how can you use this model? Well, the easiest way to do it is to then say, okay, we're going to use just to test a single molecule. And what I've done here is typed in a SMILE string for a novel molecule. We import that using the RD kit and create a new data frame. So this is my smiles.df1. We have the SMILE string in there and an ID. And the important thing is, again, that you're going to you need a unique identifier to allow you to match this up with the other properties that you're going to calculate. So here we calculate the fingerprints of that molecule. We do the same thing in terms of physicochemical properties using the evaluate program as shown here. We then combine them as we've done before using the ID as the key, and then select the properties we want to use for the prediction. So these have to match the model, and then finally we use it to predict the activity of that molecule, and it predicts it as being Ames positive, and then we can also print the probability, as it were, and as you can see, it's about 80-20 or whatever in prediction, the confidence in that prediction. You can do the same thing with a file. So here we've created a new variable where we have path to a file. We can do exactly the same. I've combined all of these now into a single block where you're calculating the properties and etc. And you'll see that eventually it looks like this. Calculate fingerprints as before, and then use that file to predict activity. And again, you can see here, I've just shown you the results. So here molecules, all 7,500, you can actually just send the model. So here, show you, you can, that's just a text about it, import the Python modules you want. But here, rather than building the model, we're just importing the saved model, which obviously saves us a huge amount of time. Again, now what we can do is use it to predict the activity of a smile string, shown here, calculate the properties as before, merge those two data frames together, and then finally do the prediction. And as you can see, quite happily, you've got the same prediction as we did before, but again, this time with the same probability. You can do the same thing with a file and predict the activity using that. I'm not going to do this for the file because this file actually contains about another 4,000 structures, which would take a while. So I hope what I've shown you here is a whistle-stop tour or introduction to Jupyter Notebooks. I think the attraction about them is that from a non-programmer's viewpoint, it's possible to add in comments and things which allow people to understand what you're trying to do with the various bits of code. You can, as I say, you can interrogate the notebook by asking it. So here, go back. You can, at any point, you can just say, well, what does this look like? And here, this is the mylogp field, gives you details of all the numbers that are in there. And by just commenting them out, you can get rid of that again. So I've finished more or less what I wanted to say. All of these notebooks are available online. They're all available at this URL. There's also another one that uses various chemical models to predict bioactivity as well. And I think, as I say, I think the nice thing about them is it's relatively easy to share them and for other people to build on them and use them in their own way. Okay, thank you.
Thank you, Chris. I have a couple of questions. So,
okay.
One, firstly, how long did it take you to get to grips with this?
Actually, it's relatively straightforward. As I say, I come from the cut and paste school of programming, and you find that things like on the RDKit website, there is a cookbook of recipes for doing various things. So if you want to import a file or whatever, there'll be a little module you can use to just cut and paste to do that. If you want to manipulate a data frame, there'll be a module that shows you different ways that you might want to cut and slice a data frame up. So it's actually really easy to do, to start with these things.
I feel inspired.
Yeah, but the other thing is that the user community is really positive and really very, very helpful.
So a number of the programs that you use were not actually free. So things like MOE and I assume the Chemaxon Evaluate program. So do you have recommendations for free versions that you might want to consider using?
You can some of those things you can calculate using. So OpenBabel will allow you to calculate things like logP, polar surface area, obviously molecular weight from various places. I think the only thing that is problematic is tools for calculating pKa, and I'm not really aware of any really good ways of doing that in a free way.
Right. Yes, I think that's something I've come across before.
But there are, because you can use Subprocess to access command line tools, you can actually use a whole variety of things. So there are this thing called PerlMol, which is a whole host of chemomatics tools written in Perl, which you can access from a command line. So it's it gives you huge flexibility to use a whole variety of things.
I had a couple of questions, Chris, as well. Mark here. One was about, I just wonder, a lot of chemists obviously have got into cheminformatics through Pipeline Pilot and possibly KNIME and things like that. I don't know whether you've played with those, and but if you have, can you sort of compare and contrast?
I found well, Pipeline Pilot is not free, so it's I've only used it a very little bit. KNIME I've used a little more, and providing you can find nodes that do what you want them to do, then I found it relatively straightforward. I found writing KNIME nodes very hard work.
Right. Okay.
So I think they probably serve different functions. I think if I wanted a tool that sat on a server somewhere that did a repetitive process for, I don't know, importing structures or updates from databases and things like this, then KNIME would be perfect for that. If I wanted something to sit on a chemist's desktop and allow them to try things out without a IT support, then I think Jupyter is probably better. Particularly if you want to use it for, if you like, things, prototyping ideas and things like that.
So this question of sharing models, would it be possible to have, can you unpick the model and find out what was in the test set, or do you not need to know what was in the training set at all?
You don't need to know what's in the training set. You do need to know what data fields are used to build the training set. So you would need to know the notebook itself. As to whether you can unpick them, I've never tried it, so I don't know. It is stored in it's not stored in a binary format or anything like that. So I guess in theory you could do, but all you would have is the descriptors, I think, rather than the
actual structures.
Yes.
Yeah. In actual fact, you've also got around one of the questions which comes up a lot, which is, in effect, creating a spreadsheet with structures in rather than smiles.
Yeah, you can do that. As well, I showed it actually. That just uses the RD kit to help import things into the data frame. Calling it a spreadsheet actually is probably doing the data frame a disservice. It's actually much more powerful than a simple spreadsheet. I basically barely touched the surface about what you can do with it.
I noticed that you mentioned the importance of the ID number a lot.
Yeah.
I guess so. In KNIME, I suppose, or Pipeline Pilot, people are often sort of adding columns to a data set, and sort of not needing to worry too much about ID numbers for merging, at least in a simple pipeline. But on the other hand, that, at least in my experience, can sort of start to lead to difficulties in reusability of things, because you've sort of assumed that you've got extra columns there, which if you tried to reuse that bit of code you might not have, sort of thing. Whereas I just wonder whether it might be a lack of discipline on my part, whether there's something inherently helpful about this that promotes reusability.
From my point of view, it's come about because I've had problems in the past where you have a sort of a spreadsheet of structures. You do a calculation, and perhaps one or two of the records don't calculate or have an error, and so you end up finding that you've not actually got the same number of results as you put in, and then trying to pair them up afterwards becomes a real pain. So having this unique ID allows you to separate and then couple things together at a later date if you want to.
Right. Yeah.
Are you generating the ID? I mean, are you manually curating the IDs, or are you using something to generate them?
in the examples that I've given you here, the data files all have a unique ID in them. I've just copied that into a field and I've called it ID number. If there's no ID in there, then I put a unique ID in there, and I tend to keep it as simple as possible.
You talked about importing various. I'm not quite sure what you call them, but where you were importing NumPy and various things like that, code blocks or subroutines. I'm not quite sure what right.
Well, they're all modules within Python. Yeah, they're both NumPy and SciPy offer just about everything you could want to use in scientific programming.
Right, and in terms of the thinking about reproducibility and stuff like that, when you're packaging things up, if people are calling, if somebody comes to look at this sort of several years down the road, are they going to be importing a subtly different version of some of these code libraries?
Yeah, it's one of the things I probably should have mentioned. What I do out of habit is to put the version number. I don't know if you can see on the page now.
Yeah.
I put the version number for each of these. In practice, I've not noticed differences, but I could imagine things, particularly things like machine learning models and things like this, they could be updated and you might get subtle differences. But by putting in the version numbers, then people know if they want to reproduce the results exactly, they can do that by using these versions of each of these libraries.
Interesting. Yeah, that makes sense. A really noddy question, going right back to the beginning where you were talking about using pip to install Jupyter.
Yeah.
You talked about a command line, I think, doing that. That's just a sort of C prompt on your...
It depends what platform you're using. So I tend to work in the Unix, and in a Unix, it's just pip install Jupyter. I think if you're working on Windows, that Anaconda is probably the better choice for installing Python. They do very similar jobs, but there are issues under Windows which Anaconda, I think, seems to sort out better.
Right.
And you don't have to have Homebrew installed first.
Not for these. I mean, there's some of the cheminformatics toolkits you may need to install independently.
Okay. Well, have you got any more questions, Mark?
No, I don't think so. Thank you.
Okay.
That was great. Thank you. Very interesting.
I think so. A big thank you to Chris. It's been really interesting.
Okay, great. Well, if you send me the URL when it's up, and then I can use that as a starting point. Try